Okay, good afternoon all. I'm Jaime Corsetti. Today we'll present you our latest work, which is also a CVPR paper titled Functionality Understanding and Segmentation in 3D Scenes. So we got second place in the task-driven affordance grounding task in this challenge, and so now I'm going to present our work. So first of all, a brief recap on the task. So in this task, we are given a 3D point cloud and a set of RGBD post frame, along with a task description that describes an action to be taken in the scene. The objective is to segment the functional object in the scene, that is the object that allows us to perform that specific action. So this task is challenging because reasoning must take into account the spatial relationships that are mentioned in the prompt, and also the size of the point cloud is very high because the resolution is very high. So the cost of processing this point cloud is quite prohibitive. On the other hand, this task can be easily applied to, for example, robotic assistance. So it's quite important in my opinion. So our very related work to this task is the classic open vocabulary 3D segmentation, which by now it's a well-established task in which object has to be segmented in a 3D scene given a textual query. Now, differently from functionality understanding, usually we have much simpler prompts, for example, that only describe a single object, and also the point cloud have a much lower resolution. So example works in this topic are OpenMass3D and Lerf. In fact, in SimFun3D, it has been shown that these methods perform quite well in functionality understanding, even when there is specific fine-tuning on functionality understanding data. So in order to work on this, we designed our own method, which is called Fun3Du. So in a nutshell, our method is based mostly on 2D vision language models and adopts a chain of thought reasoning with the LLM, along with a hierarchical object segmentation. Notably, it is training free in the sense that we do not train, especially on specific task annotation. So we only use pre-trained models. So we start with the task description understanding module. We are given D, which is the task description, and we wish to find two specific objects from it, or two specific object names. The first is the functional object, which is the name of the object we want to segment. And the second is the contextual object, which is the object that is partially related to it. For example, the object that contains it. So in this case, we have opened the bottom drawer of the cabinet with the TV on top. We do this with an LLM. And the functional object would be the drawer handle or the handle, and the contextual object is the cabinet. So we decompose the task in this way. So here we have another example of what we ask to the LLM. So we ask to decompose the prompt in order to get first the task solving sequence, which is a sequence of steps to carry out in order to solve this action, and then the name of the functional object itself, and finally a kind of hierarchy of the object that are related to the functional object. So for example, in this case, we have opened the bottom drawer of the nightstand with the red table on top. The hierarchy would be nightstand and drawer. And in fact, we get this object, which is the function as a drawer handle, and from the list of the hierarchy, we get the first name, which in this case is the nightstand. So then we want to find an approximate location of where the object of interest is located. So in order to do that, we consider all the frames in the scene, which are provided along with the 3D data. We get the name of the contextual object, and we apply an open vocabulary segmentation pipeline to get all the objects in the frame. So in this case, we get a set of masks of this specific cabinet. Here in particular, we use grounding Dino plus SEM to get the masks. Now, one problem is that for each scene, we have really a lot of views, usually around 2,000 on average. So processing all these views in the next step is very costly. And moreover, probably we do not actually need all of them because some of them will be bad, some of them will be good. So for example, in this case, I'd like to have some method of understanding which views are good, so which views are worth processing and which are not. Now, to do this, we designed this score-based view selection mechanism, which in itself actually is quite simple. So given a view, we consider the mask, and we consider the distribution of the angle of each pixel with respect to the center, and also the distance of each pixel with respect to the center. So then we design two scores, which are based on the inverse of the Kullback-Lever distance between the probability distribution of the distance and of the angle to get with a uniform distribution, which is the reference. So here the idea is that if an object is very well visible, then both distribution will be close to the uniform, because if an object is well visible, it means that it is quite centered on the image, and it's well distributed around the center. So we define these two scores, which are the distance score and the angle score. We also consider a semantic score, which is obtained from the segmentor. So in this case, we use SAM. So this is the confidence score given by SAM. And finally, we average with hyperparameters all the score to obtain a single one after normalization. So in this way, we can rank all the views we have, and we select only the top K, specifically the top 50 in our default setting. So this is an example of what should happen. So here I got all the masks for this object, for the nightstand. I highlighted the masks in the image, and I'm showing you the mask with the higher score and also the one with the lower score at uniform intervals. So this is what actually should happen. You can see that with high score, I'm getting masks in which the nightstand is very well visible, while on the other hand, with low score, so probably not selected, I will get the nightstand, which is quite difficult to see. Okay, at this point we have a lot of views, not so many, a lot of views of the object of interest, which possibly is well visible, and here we must actually find the functional object. So to do that, we use a visual language model, particularly Molmo. So Molmo has this unique capability of pointing to objects with a quite high degree of accuracy. So we prompt Molmo with a prompt that is built with the functional object name and the task description. So in this case, it would be point to all the drawer handle, which is the functional object name, in order to open the bottom drawer of the cabinet, etc., which is the task description. So in this way, we get the points in all the frame, and then we run SAM together with the points as input to get the masks for each frame. Now, as you can see, we can have some noise, especially in the right-hand cases. So here you can observe that in this case, not only the knobs are segmented, but actually all the drawer. So in the next step, we want to fix this, and we do this by multi-view agreement. So we have all the sequences of masks of the functional object. We unproject and sum them on the point cloud, as we assume that we also have the camera poses. And in this way, we can build a heat map of the functional object in the scene. Finally, very simply, we apply a threshold in order to get a binary mask, and this would be the final functional mask on the point cloud. So these are our results compared to some state-of-the-art methods for open vocabulary segmentation. All of these are tested in a zero-shot setting, so without any training, as our method. So we report split the precision, the recall, and the IOU. In general, what we can observe for all the baselines is that they have a very high recall, but a very low precision. And in fact, what happens is that commonly they will segment the contextual object instead of the functional object. So if as prompt I'm giving to, for example, OpenMasterD, open the bottom drawer of the nightstand, it will just segment the nightstand. This is usually what happens, and we can actually see this quite well in the qualitative results. Yeah. Now, in general, our method can be accurate enough. There are, of course, some cases of error. For example, on the rightmost column, the prompt is close the bedroom door, and we can see that so there is a door and there is an object which looks very similar to a door next to it, which is a wooden closet. And in our case, our method is actually segmenting the wrong angle. But in general, compared to other methods, and here I'm showing OpenInst3D, which is the best one, compared to the other method, we can get the functional object with a quite good degree of accuracy. Here I'm reporting some ablation studies on the main architectural component of the model. So first, we have this row in which we are not using molmo plus m for the functional object. So instead of using molmo plus m, we use just an open vocabulary method exactly as we did for the contextual object. And this leads to very bad results because it looks like these methods, specifically grounding Dino and Sam, are not, AOL and Sam, not grounding Dino, are not very good at segmenting the functional object because they are very small. And in fact, this is the change that leads to the worst performance in our case. Then in the second row, we remove the task description in the prompt. So instead of asking to segment that specific object in order to do that specific action, we only ask segment the drawer handle. This also causes a big loss in accuracy, mostly because there can be ambiguities due to similar object presence in the frame. So without the task description, molmo cannot handle these ambiguities. Finally, we remove the view selection mechanism, and here instead of sampling 50 scenes with view selection, we sample 100 without view selection, and the results are quite worse. And also the computational cost is much higher. So in conclusion, we introduced the first approach that was tailored specifically for this task, for functionality understanding, and we also made a training-free approach that does not need task-specific annotations. Moreover, our method is quite easily upgradable with new state-of-the-art LLMs and VLMs, as it is training-free and is quite modular in its design. Now, of course, there are some limitations. So we observe that Fan3View performance is worse when there are prompts with ambiguous contextual objects. So, for example, if we are asked to open one drawer in a specific cabinet and there are other cabinets in the room, so this can be a case of error. Although the view selection the view selection and the multi-view agreement are usually quite good at processing at least part of this error. So moreover, since we have a lot of LLMs and VLMs, the speed is quite low, the memory cost is high. Although compared to methods for open vocabulary segmentation, it's not that bad. This is the end of the talk. If you're interested, you can find my poster on Sunday morning at number 336. This is my team, and that's it. Thank you.
Do we have any questions?
Just one very quick question. Thank you for the presentation. I absolutely love the idea of active view selection. Do you end up with a very heterogeneous set of views, or do you get like very correlated views? Could you use a single view with this method?
Okay, so the set of views is not too correlated. I mean, there can be many sparse errors, like spurious detection, but usually we have a good amount of view on the correct object, or at least on the correct object type. Yeah, we did some ablations on the number of views. Actually, the method works reasonably also with 20 or 10 views, but then the performance drops. There are some more details in the supplementary material about this. Also, we found that even if you go up to 100 and 200 views, the gain in performance is extremely slow. It's extremely slow. It's extremely small, and the method gets much slower.
That's great. Thank you.
Thank you.